Hello everyone. This week we're talking about non-experimental methods, or more loosely speaking, scenarios in which we have continuous, independent, or predictor variables. So essentially any kind of situation where we don't have any groups. Here's our big original decision tree again. And here's the smaller version, which only included continuous dependent variables, or criterion variables. We went through the left-hand side of this to learn how to deal with experimental methods, and now we're going to focus on the right-hand side. So what do you do when you have a continuous independent or predictor variable and a continuous dependent or criterion variable? So let's get rid of the left-hand side for now and look at the decisions we're going to be making for continuous predictor variables. As you can see, the questions we ask ourselves here are very similar to what we asked ourselves in the experimental decision trees. The only real difference here is that the dependent variables are called criterions and the independent variables are now called predictors, because these are non-experimental methods. So first we ask ourselves how many criterion or dependent, we'll say criterion from here on out, how many criterion variables we have. If the answer is 2, then we have to do either an SEM or similar analysis like path analysis, which is way more complicated than we have the time or energy to do. Like, I'm being 100% serious, maybe like 1 or 2 people in any given faculty know how to do this. It's super, super complicated. So we're going to ignore it. Now the other option, if you have 2 or more criterion variables, is to just do many regressions and correlations, one for each of the criterions, which is what you see done most of the time because very few people know how to do the more complicated statistics. Now, of course, because it's just many regressions and many correlations, the processes and procedures are the exact same as when you only had one criterion variable. You're just doing it more times. So then everything we're going to talk about this week is going to be on the left-hand side, the scenario in which we have one criterion variable, and then after that we have to think about how many predictor variables or independent variables we have. We'll call them predictor variables from here on out. If it's 1, then we can do a correlation, or we could do a regression. If it's more than 1, we have to do a regression. So yes, regression actually works for both of these scenarios. Actually, regression works for any scenario in which you have one criterion or dependent variable. Even if those predictor variables are not continuous, even if they are independent variables, if you're doing a full experiment, anything we've done so far, z-test, t-test, ANOVA, all could have been done using a regression. So our song for regression is actually going to be...
Anything you can do, I can do better. I can do anything better than you.
So that's basically what we're talking about. Now, so if you're wondering now why we don't just use regression for everything and not spend a bunch of time learning the other tests, I don't have a good answer for you. It's just how the field has evolved over time, and as long as published papers are still using T's and F's, we have to talk about them in courses like this. So yeah, you could have just learned regression and you could do every single thing we had talked about so far. Anything they can do, regression can do better. So first up, let's look at the simplest scenario. We have one predictor and one criterion variable. And as we just mentioned, you have 2 options here. You can do either a correlation or a regression. Let's start with a correlation. That just tells you the relationship between 2 variables. What correlation does is give us the relationship between 2 scores, the predictor and the criterion, which when we're talking about correlation, we talk about as the x and the y. The predictor is the x and the criterion is the y. Correlation is based on the idea of covariance. They're actually the same thing, to be honest, but correlation is standardized. But the overall idea for both of them is that if 2 variables are related, then the differences between people on each of those scores will be shared. So if x and y are related, then as x varies, y should also vary. They should co-vary. I'm sure you guys have seen diagrams like this before. They're called Venn diagrams, and they show the overlap between 2 seemingly different things. Here's one that's a joke for the old Simon and Garfunkel song, Cecilia. Essentially, the idea is that the overlap between people who break my heart and people who shake my confidence daily is shared by the one person, Cecilia. So it's a visual representation of an overlap between 2 things. And the logic of correlation hinges on that idea of overlap, except sadly not with pop music. Instead, we're going to overlap variances. The idea is that our predictor and criterion variables have some level of overlap in the variability. We want to know how much that is. Let's look at this another way. If we graphed all of our participants, each of whom has a score for X and a score for Y, and we find each person's place based on those X and Y values, so X values are along the X-axis, Y values are along the Y-axis, and we can draw a scatter plot to show how those two variables might be related. In this example here, we can see that if you score high on 1, if you score high on X, you're pretty likely to score high on Y. That would suggest that there is an overlap in variability in these two variables. They seem to fluctuate together, and that means overlap. So what we're going to do is calculate what's called a correlation coefficient. It'll be a single number between -1 and +1, and that will tell us two things about how these variables vary together. First, it'll tell us about the direction of the relationship, and then it'll also tell us about the degree of the relationship. Let's talk about each of those. First, the direction of the relationship. Any correlation between 0 and 1 is a positive correlation, and any correlation between -1 and 0 is a negative correlation. So a positive sign, positive relationship. Negative sign, negative relationship. In these scatter plots, we can see examples of each. As the positive correlation shows that as X increases, Y also increases. In this example, as the temperature increases, the number of beers sold increases. In the negative correlation example, as X increases, Y decreases. So as the temperature goes up, the number of coffees sold goes down. That's hot coffees, not iced coffees, obviously. If our correlation coefficient is positive, we know our data will look something like the first option. If it's negative, we know it'll look something like the second option. In both cases, there's overlap. They fluctuate together. But in the first case, they both go up at the same time, and in the second case, one goes up and one goes down. The next thing the correlation coefficient tells us is the degree of the relationship, or how much these things covary together. A correlation of one or -1 indicates a perfect fit. They covary exactly together. A correlation of 0 indicates no fit at all. There's no relationship between these variables. Intermediate values represent the degree to which the data points approximate a perfect fit. In other words, the numerical value of the correlation reflects the degree to which there is a consistent, predictable relationship between the two variables. So you can see in the top example here where it's labeled no correlation, that would be a correlation of 0. There's no indication that as one increases, the other increases. In the bottom one, you can see that there's a very high positive correlation, and that as one increases, the other increases, and they increase really consistently. One thing the correlation coefficient doesn't tell us, though, is if we have any curve or complex relationship among our data. Correlation really only tells us about straight line relationships. So for example, looking at beer sales and temperature again, if we eventually get to a point in temperature where people just don't want to leave home because it's too hot, so beer sales start to go down again, and you can see that a little bit in this illustration. You can see it sort of evening out at the very least. So in that case, the correlation won't tell us that. It'll only tell us that there's generally a straight-ish relationship going on, and it won't be able to detect this sort of curve that starts happening at a point. So to the extent that having a correlation coefficient will tell you at least that there's somewhat of a straight line in your relationship, it can tell us that that's going on, but it won't tell us anything about a complex relationship. We need another way to do that. And we're not going to get into that because that's too much for us at this point. So we're only going to use it for scenarios where we have a straight line relationship. So that's what the correlation coefficient does. The next step is, how do we get one? Well, we calculate the Pearson product moment correlation. That's the most common way of calculating correlation, and it's also just sometimes called the Pearson correlation, or sometimes just correlation. They're all the same thing. And the logic of it is the same as all of the other things we've calculated so far. We're going to take the bit that we're interested in, the signal, and put it over the noise, which is going to be some variation on error. In the correlation context, that means we're going to take the degree to which X and Y vary together, their covariance, and put it over the degree to which they vary separately. That's going to be their standard errors. So that quite literally breaks down to putting the calculated covariance, I'll show you how to do that in a second, over the standard deviation of each variable, just multiplied together. And here's the way we calculate covariance. Definitionally, what we do is we calculate the deviations from the mean for each person and multiply them together and then sum them to put them over the degrees of freedom. And then below that is just an adjusted version. We're just algebraically shortened it to make it easier to calculate. But we can actually go one better than that and come up with the entire correlation formula in one go. Again, this is identical to the theoretical formulas we just looked at. It's just algebraically adjusted to save you some time. So if you're keeping track, we now have two possible ways to calculate the correlation coefficient R. First, we can do it all in one go with the top formula, or we could use the second formula, which will require the covariance formula, which is on the bottom right here. Either way can be used. They'll both come up with the same result. So let's work through an example. Let's say we want to see if attendance impacts grade level scores in reading. So our X, our predictor variable, is how many days out of 10 students attended, and then our outcome criterion, or Y variable, is their score on a reading test that's out of 4. So first we can put the data from this example into a scatter plot, which we don't always do, but is a good idea to see if you're dealing with a straight line relationship, or if there's a curve or whatever else. This data does suggest something like a straight line relationship, so that tells us that it might be worth doing a correlation. So let's calculate the correlation of these items. First, we'll do it using the covariance and standard deviation formulas. Here you can see I've calculated the covariance, and then you can just put that into the R formula, and there you go. And then we can do it with the simplified formula, and you can see we get the same result. I encourage you guys to try doing this yourself. I think you actually have to do it in your lab assignment, so you'll get a chance, but I encourage you to try this out and see if it works for you. Okay, once we get our correlation coefficient, our Pearson correlation coefficient, or R, we can start to interpret it, but there are 4 things we have to think about as we interpret it. Of course, we know we're interpreting the degree of the relationship and the direction of the relationship, but we want to consider a couple of things. First, you've heard this before, but correlation does not mean causation. It just tells you that there is a relationship between two variables. It does not tell you why those two variables are related. Also, the value of R can be greatly affected by the range of scores represented in the data. So when you have really truncated data, like we have in this case, where it only ranges from 1 to 4 is in our test variable, that can make it really tricky to get proper correlation. So we don't change our interpretation, but we're cautious in this interpretation. And then also 1 or 2 extreme data points called outliers can have a dramatic effect on the outcome of a correlation. So in this data, we have 1 student who didn't attend class at all in 10 days. And that might be really impacting our data, especially because we have so few participants to begin with. So again, it doesn't change our interpretation, but it makes us cautious about how much we want to invest in this idea. And then finally, although correlation of like 1 would mean that, yeah, this perfectly fits. These two things fluctuate exactly the same together. A correlation of like 0.5 doesn't mean that you can make predictions about it with like 0.5 accuracy. Correlation is not a measure of accuracy. It's only a measure of the relationship. We could actually, if we square R, we could get R squared, and that'll tell us the exact amount of variance that is accounted for, the exact amount that overlap is, which is a better measure of accuracy. But R by itself does not measure how good of a prediction it is. It just measures that there's some predictive ability. Now, the great thing about correlation coefficients, and R in particular, is that they are their own effect size. So here you can see the rules of thumb for interpreting the size of that relationship. So as with D, a lot is going to depend on what you know about your population, and there are some contexts in which big difference doesn't mean as much, but a little difference in some contexts can mean a lot. So you want to take these with a grain of salt and always know your literature in your area well enough to judge whether these are appropriate. But these are the general rules of thumb about how big R is. So a small would be 0.1, a medium 0.3, and a large around 0.5. So the example we just calculated where we have 0.875 is very large. That's a very big effect. Now you may have noticed actually that we have calculated R, and we've talked about what it means as an effect size and how we can interpret it, but we haven't actually talked about whether it's statistically significant. And that's because when we have a correlation, we can interpret a lot about a correlation without it knowing whether it's statistically significant. We do have to test it though in the end. So that's what we're going to do now. So we have skipped a step in our hypothesis testing. So let's go back and do that. We need a null hypothesis. And our null hypothesis is going to be essentially that there's no overlap in the variance between these two variables. Written as symbols, here's how you would put that. That rho symbol here is the population term for R. So this is saying that in the population there's no relationship between our two variables. And of course, anytime we're doing a hypothesis test, we need a sampling distribution because we're always connecting our sample to our population. Now our sampling distribution here is going to be a little bit different. It's the sampling distribution of the relationship between our variables. So it's the relationship between these two variables if we had all possible samples of this size taken from this population. But there's a problem with that. The shape may be skewed depending on what the population relationship is. So let's say the population correlation between these two variables was 0.6. That means that as we pull the samples out, the samples are going to start to pile up around 0.6. Remember how sampling distributions work. But because R is truncated, the tail can't go beyond 1. So as it starts to pile up around 0.6, as you can see in this illustration, it's going to start getting lumpy at the top end. And the tail is going to extend down to the negative end, and that's going to mean that we have a skew. So we don't have a normal distribution. And that's a problem. And because we need a normal distribution in order to be able to make those hypothesis tests. So what are we going to do? Well, what statisticians have done is come up with a process in which we transform the sampling distribution for R into a normal sampling distribution, which is called Fisher's Z prime distribution. And it's done through ways that I'm not even going to get into. But they transform all the possible scores so we get this distribution called Fisher's Z prime. That'll put all the R values along a Z prime distribution, which is exactly the same visually for us as a Z distribution. But then we have a problem again because we now have a sample that we're trying to match to this sampling distribution. So in order to do that, we're going to need a version of the Z prime distribution that accounts for degrees of freedom. So what is similar to Z but accounts for degrees of freedom based on a sample?
T for 2 and 2 for T.
That's right. We're going back to the t-test, ladies and gentlemen. So what we do now is the R distribution is essentially transformed until we can get to t and use that to judge its significance. So here's the formula for t that we would use to get a t value to judge whether our correlation is significant. And of course we would use the degrees of freedom, which is n-2 for a correlation. But here's the beautiful thing. Statisticians have actually already done all this work for us and long ago figured out all the critical R values that would match up to critical T values. So we actually have an R table and we don't need to calculate T. The computer has essentially calculated it for us. So we can go right to the decision stage here without taking that interim step of calculating T. So we're going to look R up on an R table and get critical R to find significance, same as we did for all the other tests. And as with all of our tables, what we're going to need is the degrees of freedom, so this is n-2, the alpha level, which is, we're going to set at 0.05, same as we usually do. One or a two-tailed test, we're going to set it as a two-tailed, as we usually do. Note, because we're using essentially a t distribution, it's the same as t, we can have a two-tailed test, so that's what we're going to do. And then, of course, we need our value of R to compare. So we look along the top for our alpha level. In this case, it's conveniently split by one and two-tailed tests. So we find 0.05 in the two-tailed section. And then along the rows, we're looking for degrees of freedom equals 3 because we had 5 participants and 5 minus 2 is 3. So that's here. Our critical R is 0.878. And of course, our found R, the one we calculated, is 0.875. So that would suggest it's close, but not a significant correlation. So we would fail to reject the null hypothesis in this case. So here's how that would be reported. Again, how we'd report it if we were doing it by hand, and then how we would see it reported in print by people who have access to computers. Now, the thing about correlations is that because we have computers, we can actually run a bunch of these at the same time. If we have multiple predictor variables, we can see how they each relate to each criterion at once. We can also see how they all relate to one another. So it's actually pretty rare nowadays to see an R reported like this. It's much more likely that it's much more common to see the R reported as part of a correlation matrix or a correlation table. And here's what that looks like. So this is taken from a study that I did that was looking at kindergarten science intervention. In this case, I had multiple dependent variables, which you may remember means that I had to do a multivariate ANOVA, which we haven't and are still not going to talk about. But one thing that's important if you're doing a multivariate ANOVA is checking the correlations among your dependent variables. Essentially, we want to know if any of the variance in our dependent variables is shared, or does one dependent variable predict another. The particulars here aren't super important. What matters is that I had to see what the correlations were, and this is how you report that information when you have more than 2 things you want to correlate. Now that sounds confusing. I thought correlation was only for 2 things, you're thinking. Well, it is. Each of these correlations is one thing with one other thing. But because we can do so many at once with a computer, it's often helpful to have a correlation matrix. And that will tell you how much each thing correlates with each other thing, how much variance each group shares with one another. So here, both the first row and the first column labeled, or the column labeled 1, is PPVT. That's a general vocabulary measure. The second row and the column labeled 2 is science vocabulary. That's science-specific vocabulary. The third row and the column labeled 3 are both concept knowledge. That's knowledge of science-related concepts, etc., etc. You see where this is going. So everything in that first column is the correlation of each row item with PPVT. The first one is a blank or a dash because it's PPVT with itself, so that's not a thing. It's 1. We don't have to report that. So we move on to the second row, and the correlation between science vocab and general vocab is 0.56. That's the R value, or the correlation coefficient. The 2 asterisks beside it mean that it's significant at p is less than 0.01. So here you can see we've set a more stringent alpha than we typically do. Then the next one down, concept knowledge is correlated with general vocab at 0.55, again significant. And so on and so forth all the way through the matrix. Now we only ever have half the matrix filled out, like here, and can you guess why? I hope you guessed that it was because the other half would be an exact mirror of this, right? We only need to report each correlation once, but as we do them, they would all end up being the same. I mentioned earlier that regression can do anything that T or ANOVA can do, and that's partially true for correlation as well. Correlation is not actually limited to the scenario in which we have one continuous predictor and one continuous criterion. Instead, we can actually use different types of correlations, besides Pearson's R, to calculate the relationship between categorical variables. The point biserial correlation is used when you have a categorical predictor and a continuous criterion. This is basically the experimental or quasi-experimental situation that we've been working with the past 2 weeks. Now, the point biserial correlation is not the same as doing a t-test, and a t-test is usually better in that context. But there are some times when you just want a correlation, and that's when you use the point biserial. The good news is the point biserial correlations are exact same Pearson correlations we just calculated, like exactly the same. When writing it up, we would say that we did a point biserial correlation, and that's just a different name to theoretically differentiate the 2 scenarios, even though it is the exact same calculations for the exact same test. Next, we have what's called the Spearman correlation. It's used when you specifically have at least one ordinal variable. You'll remember that those are ranked variables, ranked categories. So you can use it with continuous variables. You can also use it with continuous variables, even if they're nonlinear. But to be honest, nobody really does that because regression gives you better nonlinear options. So usually you only see Spearman's correlation when you have ordinal variables. This one does have different calculations in the Pearson or point by serial, but it's uncommon enough that you're okay not knowing how to calculate it. So we'll just leave it here that it exists and you know it exists. And then finally we have the phi coefficient, which is used when you have two categorical variables and they each only have two groups. Again, this is pretty uncommon and we don't often see it, so we're not going to look at how to calculate it. So that covers correlation for when we have one predictor and one criterion. So we're still in this little vein here, but now we're going to look at option 2, regression. Regression is very similar to correlation, except it's much more explicitly about the predictive element rather than the shared variance, although there is that too. We're going to start by looking at simple regression, which is the version you use when you have one predictor and one criterion. It is, for all intents and purposes, exactly the same as correlation, the prediction of one variable from knowledge of one or more other variables. And it's also sometimes called the line of best fit. The logic of simple regression is exactly the same as the logic of correlation, that we want to know if there's some overlap between the variance in our x and y variables. Regression is going to do the same thing as correlation, it's just going to do it in a slightly different way. To explain that, let's start with an example. Here we can see that the older a plant is, the bigger it generally is. Let's imagine that we wanted to buy a rare plant to sit in our living room window. We find a plant on the internet, but we need to know whether it will fit in our window, and we can't tell the size from the picture. But we do know how old it is. A correlation would tell us that the two are related, but now we want to predict it exactly from the size. In other words, we want to take the correlation and expand it to get a reasonable guess of what the criterion would be at each level of the predictor. So prediction is really the central purpose of a regression. You're estimating the variable y from variable x. What we're doing in regression is we're finding the equation of the line that best predicts the y variable or criterion variable. For the plant in our window, we could look up the age in the chart and see where the line falls, and that's where we would predict the size of the plant to be. Now, for educational research, we don't generally use it to predict a single point. Rather, we're more interested in general predictions, how socioeconomic status predicts academic achievement, how parenting style predicts ADHD diagnoses in children, etc. But what this line does, even if we're not predicting a specific point, is give us an idea of what the criterion should be at each level of the predictor. So the idea is we run a study, and from that we get a regression line, and then theoretically we can use that regression line to generalize this study to the broader population. As teachers, you would be able to get a rough estimate of the outcome even if you only knew the predictor. In that way, simple regression doesn't really add anything beyond correlation because specific outcomes and errors aren't really applicable to people the way they are to plants. But simple regression is an important thing to understand before we move on to multiple regression, which is new and does do interesting things. So what we're doing in regression basically, especially for simple regression, is figuring out what this line is. So even if we can't predict a specific individual's outcomes, we want to get that sort of general prediction. Now, what that line of best fit does is it gives us an idea. It actually specifically gives us the best possible idea for prediction, because that's what the line of best fit means. It minimizes the amount of error in our prediction. But minimize does not mean eliminate. So there's always going to be some amount of error. And that's called prediction error. It's the difference between the actual score of y and the predicted score of y. So in the situation where we do a study, we collect a bunch of data, and then we get a regression line from it, there's going to be some error around that regression line. It's not going to predict every one of the outcomes that we have already measured. In other words, within our data set, our line is never going to perfectly match the data. We're not going to predict any score with perfect accuracy. There's always going to be gaps where our actual data is and where our line would have predicted that data was. That's prediction error. But even with prediction error, we can get some good information from the line of best fit. From the slope of the line, we can tell what kind of relationship it is. When there's no correlation, like in this first picture, we can see that the line would be totally flat. When it's a positive correlation that's not perfect, it's a big slope but with a lot of error. And when it's a high correlation, we get a big slope with very little error. So the slope of the line as best fit is really our best way to get the same kind of information that we get with correlation. So, I mean, again, it is basically the same kind of information, but the line of best fit basically gives us a more precise way of estimating it, is a good way to say it. Actually, you know what it does that's different from correlation is I mentioned that correlation doesn't give you accuracy. What this does with prediction error is the prediction error gives you that accuracy that you didn't get with correlation, or you had to square the correlation coefficient to get. So that is something that regression does that simple regression does that correlation doesn't do. But otherwise, it's basically the same information. Brief aside here to talk about terminology. We can say either we are predicting y from x or regressing x on y. I sometimes find this a little confusing, so I thought you might too. So the key here is that if it says regressing on, then x comes first. If it says predicting from, then y comes first. So whatever we call it, what we're doing in regression is getting a line, which hopefully you may remember from either high school or teaching. To get a line, we're working out an equation. We're looking for the equation of the line of best fit. And all the equations fit the form here. Y hat, that's the predicted value of y. Sometimes people write it as y prime, means the exact same thing. And that equals a plus bx. Now within that, what we want to find as researchers is the numbers that we can use for a and b. A is the intercept, which is predicted, which is the predicted value of y, or y hat, is the y hat when x equals 0. In other words, it's the predicted place where the line crosses the x-axis. B is the slope, that's the angle or steepness and direction of the line. In order to calculate A and B, we can actually do that with very little information. We need the correlation coefficient, the standard deviations, and the sums of the variables, and the number of subjects, of course, our number of participants. Let's use the same example we use for correlation. We want to predict test scores from attendance. Since we need B in order to calculate A, let's get B first. Okay, so B is going to equal the correlation coefficient times the standard deviation of y divided by the standard deviation of x. And then once we have that, we can go ahead and get A, which you guys should all practice, but I have gone ahead and done, and works out to 0.686. So that gives us this as the line of best fit. So we can insert any x variable we want into there, and that will give us the best prediction of where the y value would be. So if we had a class of students and we did this test with 5 of them, and then the next year, I want to do this unit again, but I have a student who only attended 5 classes, I want to know what their y would be, you can go through and calculate that. But let's assume that you don't want a specific predictive value. Again, for 99.9% of social science research, you don't want that. What you want is a general interpretation. And for that, what we want is that b value, that slope value. So we need to get A to get the line, but B is really where the interpretive meat lies, so to speak. So then the way we interpret that is that for every unit increase in Y, we anticipate Y to increase B units. So in our little example, let me put that in more meaningful language. For every class attended, we predict the score on a test to go up 0.219 points. So for every additional class you attend, you would expect your test score to go up 0.2 points. So when you hear reports of like breastfeeding increases IQ by X points or whatever, that's what they're interpreting. They're interpreting that B value. Anytime you hear something set up as when you include, when we measure this, it increases whatever by whatever, B is what they're interpreting there. So that's all well and good. We found the equation, we can interpret the B. But what about statistical significance? Now, when we talked about statistical significance, what we're talking about with regression is whether that slope, or b value, is significant. How do we test whether that slope is significantly different from 0, which is what the null hypothesis is? Remember that a slope of 0 would be a flat line. So testing this is the same as testing whether there's a relationship, and we're going to use the t-distribution. So you're already thinking this now. Does this sound exactly the same as whether r is significant? Yes, but it's only exactly the same if there are two variables, if we're doing a simple regression. So the calculations are a t-distribution, and as you can see here, you'll notice that it is what it usually is. It's the signal. In this case, the signal is the slope, and then it's over noise, which, as you can see, we have to calculate the standard error, and that's the part that's a little tricky. So what we're looking for is the standard error of the estimate. That's the standard error of your B value. And what it is it's the standard deviation of the prediction errors around your proposed line. So it's the average dispersion of data points around the regression line. And so it's a standard deviation of actual y-scores that we have measured around the predicted value that we would have anticipated. It's a little tricky. It's not that it's hard. The toughest part is really that we have to find the sum of the prediction errors. So we need to find the y-hat for every single x value we have so that we can compare that to the actual y value and then sum them. So let's take our previous example and work through how we do that. Okay, so let's do that. We have our line here. This was the regression line that we had found before. And so we can work out the y-hat for every x point, which I've done here. So we've put every x variable into that equation and come up with the y prime for everyone. As you can imagine, as you start to get more and more participants, this gets extremely frustrating. But then we can use that to calculate standard error, and once we get that, it's pretty simple to get. And then once we have the standard error, we can calculate the t. And of course, once we have the t, we can look it up in a t-table, the same as we've always done. Alpha equals 0.05, two-tailed, and our degrees of freedom is still going to be n-2. So looking that up in the table, and as you can see, looking that up in the same t-table we've been using this entire time, you can see we have a critical value of 3.18, so we would fail to reject the null hypothesis. Before we go any further, I should mention that like all our other tests, regression has some important assumptions. First, like correlation, it only really works on linear relationships. 2 is the assumption of homoscedasticity. That means that the spread of errors around the line should be the same at all levels of the x variable. You can see an example of a violation of the assumption of homoscedasticity in the illustration here. At the lower end of x, the data is a lot more compact, and then it's more spread out at the higher end. That's heteroscedasticity, and it's bad. Although it is my absolute favorite statistics word, so it's got that going for it. And then finally, the errors have to be normally distributed. In the previous examples we've looked at, we've seen that the scores have to be normally distributed for f and t, etc. But here, that's not a requirement. Only the errors have to be normally distributed. And even then, it's pretty robust to that violation. So in regression, though, it's not super robust to violations of the other two. But the good news is that they're both fixable. But how you would go about doing that is pretty complicated, so we're not going to talk about it, but it can be done. Okay, back to the example. The way we'd write that is with the b and the standard error for b, and then the t degrees of freedom and p-value. So a couple of things here you should be noticing. The b and standard error always have to be reported together. However, if you put them in, you can put them in a table rather than writing them out like this. That's totally fine. If you have multiple independent variables or predictor variables, or you're doing more than one regression in a study, then you'll be putting them in a table, and when we talk about multiple regression, I'll show you what that looks like. The second thing is that the b and standard error always have to be reported together. Without the standard error, the b means nothing. They're buddies, and they always need to be together. And then finally, you may notice that the p-value that we got from the computer here is the exact same as the p-value from when we did the correlation with this data. That's because when you only have one independent variable or one predictor variable, the hypothesis test for criterion and for correlation and regression will give you the exact same information. There is absolutely no added value to testing a regression if you've already tested a correlation on this data. You already know the p-value for that regression. So for me personally, I don't typically do simple regressions for that reason. It's very rare that it's helpful to have that extra predictive element of it. and it's a lot easier to just square R if I want accuracy. And for broader trends, correlation and simple regression are just, they're equally helpful, and correlation is easier to get. It's also, I think R is more intuitive. So when I only have two variables like this, I usually go for correlation. Now, I mentioned a second ago that B and standard error always have to go together, and that's because B, like the mean, can't really be interpreted without a measure of variability beside it, especially because B is measured in whatever skill your Y variable happens to be in. In our example, we were saying that for every one class attended, scores on the final test out of 4 increased by 0.288. As teachers or researchers who defined and made that final test, theoretically, that might mean something. But for most of your readers, that isn't super useful. What does it mean that you go up by 0.288 on a test? That's nothing. So there is another way that we can provide that information that's more intuitive and understandable, and that's by using a standardized version of B, which is called beta and represented by the symbol you see there. Basically, if you transform all your individual scores to be on one standardized scale with a mean of 0 and a standard deviation of 1, those are called Z scores, by the way, but they're really easy to calculate, but we won't bother, so just know that. But if you do that and then you run a regression, you will get a standardized score. We could do this by hand, but we really don't have to, because most statistical software packages will provide both the B with a standard error and the beta for any data set. So you'll never have to calculate beta, but you will have to interpret it. But the beta means that for every standard deviation increase in X, there will be beta standard deviations increase in Y. So when you standardize the data, the intercept is always 0. But since we never cared about the intercept to begin with, we just cannot care about it. We can continue to not care about it. So as you see here, I've converted it and replaced it with a beta, and you can see here that our regression line is now saying for every standard deviation increase in X, Y increases 0.875 standard deviations. And you may notice that this correlation coefficient is this beta is the exact same as our correlation coefficient. And that's because I pulled this from our example data. And guess what? Regression and correlation, as I've been saying, provide you with the same information. It's just the correlation coefficient when you standardize it. There's really no added value to either of them. Choose whichever one your heart desires. Okay, so that covers the simplest scenario, where you can do correlation or regression and get the exact same results in either situation. Typically, like I said, I prefer to do correlation, and that's also what I find most common. That's what I see most often in the literature. You very rarely see simple regression anymore, and when you do, I find it's from people who don't really understand that they're the exact same thing, so they report simple regression like it's somehow more stringent, but it's the exact same thing. But this is not my statistics therapy diary, so let's move on. Now we're going to talk about the more complicated scenario in which we have two or more predictors. We can't use correlation here, so we're going to focus exclusively on regression, and a more complicated version of regression actually called multiple regression. Multiple regression is very flexible. It's really the one where we really get to say,
Anything you can do, I can do better. I can do anything better than you.
Oh, you can't.
Yes, I...
So it's also, unfortunately, very complicated and difficult, both to calculate by hand and really to even visualize. You remember the logic of correlation and simple regression was that they share some variance and we were going to figure out how much. Well, for multiple regression, we're still talking about this, but we're going to expand it a little bit. Now, in this scenario, we have two possible predictors that share variance with each other and with a criterion variable. So let me turn this into an example to make it more clear. In this example, our Y variable is going to be reading comprehension, or scores on a reading comprehension test to operationalize that. Our first X variable is going to be background knowledge, how much students know about the topic of the reading passage they're supposed to be comprehending. And then our second X variable is going to be SES, that's children's overall socioeconomic status. And what we want to know is how well background knowledge and SES predict reading distinct from one another. Let me explain what that means. This blue section is the shared variance between SES and reading comprehension. In other words, how much SES predicts reading comprehension. This red section is the shared variance between background knowledge and reading comprehension. In other words, how much background knowledge predicts reading comprehension. This purple section is the overlap, that is, how much variance is shared between all three of background knowledge, SES, and reading comprehension. And this is really the key point of this entire exercise, that we can put these two predictors together and assess both how much they contribute as in an overlapping way and how much they contribute uniquely. In other words, if we know each of these red and blue spots, we know the amount that, say, an intervention targeted at background knowledge but not SES would impact comprehension by itself. This might be clearer if I redraw it slightly. Okay, I've redrawn it to show what would happen if background knowledge and SES overlapped a lot more. And so what this is saying is that background knowledge and SES together contribute to almost all of the shared variance with reading comprehension. So in an intervention that targeted background knowledge, it might end up reducing SES because SES by itself doesn't contribute that much unique variance. And you can imagine why education researchers love this idea. If we could find scenarios like this one, where something we have very little control over, like SES, can be influenced by something that we do have a lot of control over, like building knowledge or selecting books that tie into children's previous knowledge or whatever. And essentially we can work with background knowledge, which is great if it overlapped so much with SES, because SES often feels like it's hopeless for us to help, at least as individual teachers. So that's why finding out why the purple section is handy. But it's also really handy to find out those red and blue unique variances. Let's go back to the other illustration where they're bigger so I can explain that part. If you remember way back when we talked about nuisance variables, we talked about how you could sometimes statistically control for things. And that's what this is, partialing out the unique variance relative to the total variance. Looking at the impact of background knowledge while controlling or partialing out variance due to SES. Or the reverse, looking at the impact of SES while controlling for or partialing out background knowledge. So anything that you're interested in, if you think there's a nuisance variable, you can measure it and then control for it, so you're only looking at the variance that's due to your variable of interest. Theoretically, if we could measure every single aspect that contributes to reading comprehension, not just background knowledge and SES, but language skill, attentional capacity, noise level in the classroom, or whatever, we could account for 100% of the variance within our criterion variable or outcome variable. And then we could, theoretically, fully explain the concept of reading comprehension through just a bunch of different X variables. Of course, in reality, that's not possible. There's way too much noise in human existence for that to be a real thing, or even a useful thing. And also, throwing things into a regression that we don't have a good theoretical reason for is just generally a bad idea. We call those kitchen sink regressions, because you're just throwing everything in there. So in general, we're looking for the simplest regression that explains the most variance in our criterion variable. That's the overall principle of multiple regression. And then we can look at how much each uniquely contributes and how much they together contribute. Now, mathematically speaking, it's much more complicated and less intuitive. Essentially, we're coming up with a regression line, same as before, but it's going to have multiple slopes for multiple x values. So on the right, you can see it also really stops being visually intuitive as a line, per se. So I'm honestly not even sure we could draw it if we had more than 2 x variables, which of course you can have. You can have an infinite number of x variables. So as you can probably imagine, we're not going to calculate this. It's too complicated. But we are going to work on interpreting it. So to interpret multiple regression, we're focused on 2 things. First, we're going to have the overall amount of variance explained in Y by the collective X variables. That's what's called the overall model. Regression, when you put a bunch of different X variables in, it's called the model. And so first we're going to look at that, and then we're going to talk about each of the individual specific slopes. So as we interpret these, we're going to do it through an example. Let's take one that we're talking about. So I'm interested in how background knowledge and SES impact reading comprehension. So I measure 87 students on all 3 variables, and I set a null hypothesis that there's no relationship among those variables. And here's what that would look like. Our null hypothesis is going to be about the individual slopes rather than the overall model. But first we interpret the overall model. When we do that, what we're saying is how much overall variance of all these things together is explained in the y variable. So it's telling us essentially how much this purple section is in the illustration. And what it's going to give us is a coefficient referred to as big R squared, or we can just call it R squared, but we have to be careful to write it as a capital R. And it's literally the variance accounted for by all of our x variables. Sometimes people will report the adjusted R squared, big R squared, which is adjusted for scenarios where you have a lot of x variables. When you need to use one versus the other is beyond the scope of this course, but you interpret them in the exact same way. The amount of variance accounted for by the predictors, all taken together. Now, whether or not that's statistically significant, so whether or not our proposed x variables account for an amount of variance that is statistically significant from zero, significantly different from zero, is tested with an ANOVA. The null hypothesis would be that none of these variables account for a significant amount of variance. And the alternative hypotheses are, of course, many that boil down to at least one of them shows a difference. One of these things is not like the others. So the way you commonly see this reported in papers is just with a sentence like the overall model was significant R squared or adjusted R squared equals 0.08 we have here, and then F, and then the F statistic is reported just the same as we saw last week with ANOVAs. So it's the exact same F, we're just popping on a big R squared on the front of it. So then once we know the overall model is significant, we move on to examining the individual slopes and the unique variance contributed by each predictor. This is very much like simple regression. You'll get individual b's with their standard errors, or alternately you can get betas, which we remember is a standardized version, and you interpret those almost the exact same way you did for b's in the simple regression. For every 1 unit increase in x, y will increase by b units. So for every 1 point increase in background knowledge, reading comprehension will increase by b points. The key here is that last bit of this little sentence, holding all other variables constant. So it's actually for every 1 point increase in background knowledge, reading comprehension will increase by b points, holding SES constant. That means it's going to increase that much over and above whatever effect there is for SES. And again, just like with simple regression, whether that slope is significantly different from zero, or whether that unique variance is significantly different from zero, is same test. It's the same test as we learned with the simple regression. It is a t-test. Now, unlike with the overall model or simple regressions though, you don't typically report individual b's from multiple regression in text. The standard convention is to put them in a table like this. So here's how that would look. You can see here the b, that's the slope, is reported along with its standard error because they're buddies and they always go together. And then we have the t value, the p value for that t, and then what's called the SR squared. That's not always reported, but I like to report it, so I included it in here. And it's the total unique variance contributed by each variable. So in this example, we can see that although we can see that background knowledge accounts for 3% of the variance in reading comprehension, that's not statistically significant from zero. Whereas SES accounts for 7% of the variance in reading comprehension, and that is statistically significant. So background knowledge may not contribute outside of SES for this particular population. You may be already noticing how similar this is to the work we did with categorical independent variables. We start with an overall ANOVA, and then we move on to t's to compare specific groups. That's because all of these tests are part of a family of tests called the general linear model. Regression is the broadest member of the GLM, and that's why it can do literally anything we've done so far. You have a treatment or control group? Great, then that's an x variable, you can regress on your y variable. You have pretest and post-test? Great, regress the pretest on the post-test. It doesn't matter if it's categorical, it doesn't matter if it's related or an unrelated variable, it doesn't matter how many independent variables they are.
Anything you can do, I can do better. I can do anything better than you.
Oh, you can't.
So it really is, I cannot emphasize enough how much it is all the same thing. All statistical tests exactly the same. So then one last thing for multiple regression is that the one thing that can be a problem is multicollinearity. That's a condition in which the predictor variables are highly correlated among themselves. Essentially, if this green section here gets too big, it really messes up the whole measure. It impacts how big the purple section is, and that limits the amount of unique variance that it can be explained. And it's fine for them to be a little correlated. They're supposed to be a little correlated, but when it starts getting really high, it starts to be a problem. And so you don't have to worry about knowing when it's too much. This is just mostly to recognize when papers say, oh, we did this to account for multicollinearity, that you know what they're talking about. Okay, one last time, here's our big decision tree. We haven't been able to go through all of it, and of course there's more complex versions of some of these, but we have done a lot, so you guys should feel really proud of yourselves. We have covered a lot of information here. Way to go, guys!